Okay, so in this talk, I will present some fundamental concepts related to belief functions. We'll see notions of belief, plausibility, conditioning, basic rules for combination, and then also some little bit more advanced concepts, concepts related to informational ordering, cautious rule, which is a new rule I introduced some years ago, and how to reason with different frames. Okay? And these will be fundamental. The next talk is by Professor Denœux, and he will use this extensively and have a working on different frames. Okay, so a little bit of history. So theory of belief functions is a formal framework for representing and reasoning with uncertain information. It's also known as Dempster-Shafer theory or evidence theory. All these terms are synonyms. It originates from the work of Dempster in the 1960s in the context of statistical inference. Okay, so actually, this story started with R. Dempster trying to generalize Bayesian inference. Okay, he wanted to have some mechanism for Bayesian statistical inference without using prior information. Then the theory was formalized by Shafer in a famous book published in the 1976, which is cited here. And so Shafer showed that this theory was useful not only for doing statistics, but also as a general framework for reasoning with uncertainty. And it was later applied in many domains, mainly in artificial intelligence for knowledge representation, machine learning, in engineering, where there are applications in reliability, risk analysis. I could add like in your business with auditing. So there has been a lot of applications. Also, this approach was popularized and developed by Smets in the 1980s and 1990s, and he coined the term transferable belief model. Transferable belief model is basically the same thing as Dempster-Shafer theory. So the main idea, I think, behind this theory of belief functions is that it extends both logical or set-based formalisms, such as, for instance, propositional logic and interval analysis, that is to say, reasoning with sets, on the one hand, and it also extends probability theory. So a belief function may be viewed both as a generalized set. Actually, we'll see that it can be seen as a random set, say a collection of sets with probabilities attached to them. And it can also be seen as a non-additive measure, okay, generalizing a probability measure. And so this theory includes extensions of probabilistic notions like conditioning, marginalization, and set theoretic notions like intersection, union, inclusion, and so on. So an important fact to keep in mind is that Dempster-Shafer reasoning produces the same results as probabilistic reasoning, or for instance, interval analysis, when provided with the same initial information. So if you start with only probabilities and you do evidential reasoning, you get the same result as you would have if you had used, let's say, Bayesian reasoning. But the fact is that you can start with information which is less precise than probabilities. So this is why we can say that this Dempster-Shafer theory has a greater expressive power than the, say, for example, the theory of probability. Okay. So this is like the landscape of theories of uncertainty. There is not completely everything here, but most of the, let's say, contemporary theories of uncertainty are here. So we have, for instance, fuzzy sets and possibility theory. Some of you may have heard about fuzzy sets, for instance. And actually, there are some connections, okay, and I will come back to this later, between possibility theory and belief functions. Okay, we'll see that a possibility measure can be, it actually is a special belief function. Then we have theories of imprecise probabilities that instead of assigning to an event only one number, I call this probability, assign, for instance, an interval, okay, and they define sets of probabilities. There are also some connections with Dempster-Shafer theory. Okay? So it's not the same thing. I will explain why it's not the same thing, but there are some connections. Okay? Then we have, of course, probability theory is really a subset, can be regarded as completely included within Dempster-Shafer theory. And there is also rough sets. I don't know if some of you have heard about this. It's an approach for knowledge extraction from databases. And it also has some ideas in common with Dempster-Shafer theory. Particularly the idea of having some reasoning with sets and having some kind of inner and outer approximation of a set. And it has some flavor which is quite similar to some notions in Dempster-Shafer theory. So you see this Dempster-Shafer theory occupies a position of centrality here because it has connections with all the other formalisms. Okay, so let me start with the basic notions. So the first notion here will be that of a mass function. Okay, so we start with a set omega. Here in this lecture, I will, and in most of the lectures, it will be assumed to be finite. Okay, but at the end, in another lecture I will relax this assumption. But here omega is finite. This set will be called sometimes a frame of discernment. It's like the universe of discourse. And we define the mass function on omega as a mapping M from the power set of omega. So this notation 2 to the omega is called the power set. It is the set of all subsets of omega. So this is a mapping from the set of all subsets of omega to the interval 0, 1, okay, such that the sum, okay, of the images M of A for all subsets of omega is equal to 1. Okay. So we attach to each subset of omega a number between 0 and 1. The sum of these numbers is equal to 1. And usually, almost always, we will have an additional constraint that the mass, these numbers are called masses, the mass assigned to the empty set is 0. Only in some specific applications like clustering, I will come back to this tomorrow, do we relax sometimes this assumption. So this is a very simple mathematical definition. Okay. So now what does that represent? Okay. What is the meaning of that? So in Dempster-Shafer theory, a mass function is used to represent evidence about an uncertain variable x taking values in omega. So we have some variable, anything, okay? It takes some value in omega, and we have only uncertain information about x. So we want to represent that uncertain or partial information. Okay, so I will start with this example, which I will take as a running example in part of this lecture. So this is an application we developed in our lab in Compiègne, France. This is about scene analysis, okay, for intelligent vehicles. So we have a road scene like this one, and we have different sensors, okay? So we get information from different sensors, and we want to determine the contents of this image, okay? So this was developed some time ago. Now we would typically use deep learning to do that. At that time, we had another approach, which was to over-segment the image in very small regions, okay? And then we try to determine the contents of each region. So here, let X be the type of object in some region of the image, okay? We focus on some region. We want to determine what is in that region. So here, omega can be, for example, a set that we can have grass, a road, a tree, an obstacle, or the sky. Okay. You see that we could subdivide these possibilities into finer possibilities. Okay, we can always, given a given frame, a given universe of discourse, we can always split a possibility into finer possibilities. Okay. This is what why Shafer called this frame of discernment. Okay, we choose to discern only between these possibilities. Okay, but we could have define a finer set of possibilities. And later in this talk, we'll see how we can, if we have expressed our knowledge in some frame, how we can convert it, express it in a finer frame, or in the contrary, in a coarser frame. So assume that we get information, you can say evidence. Evidence basically is the same thing as facts or information. So we receive evidence from a LiDAR sensor, which is a laser telemeter, that returns the information that in that region of the image, we have either a tree or an obstacle. Okay, because we see some object at some distance, so it can be a tree or an obstacle. Obstacle can be like a car or any kind of vehicles, anything that is on the road. But this sensor is also uncertain. Actually, we assume that we have 10% probability that this information is not reliable because, for example, the sensor might be out of order, okay, or obstructed or something like that. So we want to represent this information. You see, this information is both imprecise, okay, because it tells us that we have either a tree or an obstacle, okay, but with nothing more specific. And it is uncertain because it's only partially reliable. So actually we can define, so here we have in this picture, on the right, we have the set omega with the different possibilities. On the left, okay, this is to relax. Okay. So on the left, you have this set S, which is the set of states of the sensor. Okay, and either the sensor is broken or it is working. You see that we have probabilities on this set S, okay, and not on omega. So if the sensor is working, then it tells us that we have either a tree or an obstacle. So we know, in that case, we know that we have either a tree or an obstacle. If the sensor is broken, then we don't know anything, okay? Because information from a broken sensor is meaningless, okay? So either we know that we have a tree or an obstacle, and this is true if the sensor is working, or we don't know anything. And so this probability, for example, 0,1, is a probability of not knowing anything. So we can represent this information by a mass function that will assign a mass 0,9 to the image here of working. You see, these probabilities are carried from S to the power set of omega. So the 0,9 probability is transferred to the set T and O, and not specifically to T or O, okay, just it's transferred to the set. So here I have a probability that is assigned to a set, and it cannot be split. It cannot be distributed inside that set. And the mass on omega is 0.1, so this is a mass on broken, which is transferred to omega. So you see that in this example, the mass 0.9 is the probability of knowing only that the object is a tree or an obstacle and nothing more. Okay? And the mass 0,1 assigned to omega is the probability of knowing nothing at all. So in general, what is the meaning? We say the semantics of a mass function in Dempster-Shafer theory. So this was explained in a paper. This was not really explained very clearly in Shafer's book published in 1976, but it was explained in this later paper published in 1981. And this is referred to as a random code semantics. So what is that? So assume that we receive a coded message. We receive a message, but this message is coded, but it contains reliable information about X. Okay, if you can decode the message, you will get true information about X. The message was encoded using some code. in a set of code, S. You have this set of codes. And then there is a multi-valued mapping, gamma, from S to the power set of omega, minus the empty set, that defines the meaning of the message. So meaning that if code CI was used, then the meaning of the message is that X belongs to gamma of CI. So it means if you take the message, you take the code CI, you decode the message, you get a proposition X belongs to some set, gamma of CI, and this is true. So we don't know which code was used, but we know that each code CI had a chance, some chance, PI, of being selected. So the code was chosen at random. And then the mass M of A is a probability that the meaning of the message is X belongs to A. Okay. And so this probability can be computed as a probability of the set of codes C such that the meaning of the message, if the code C was used, is A. Okay. So coming back to the previous story, it's like you receive some message about the contents of a region of the image, and you have two possible ways to decode this message. Using one way, you get the message that there is either a tree or an obstacle. If you use the other code, you get the meaning of the message, which is we don't know anything about what is in the image. And you don't know which is true, okay? But you have a probability 0.9 that the first code was selected. So you see here the probabilities are over the meanings of a message. Okay? We receive some evidence, but the meaning of that evidence is uncertain, okay, and is quantified by probabilities. So you can say, okay, this story of random code is not realistic. Usually we don't have information like this, okay? But the thing is that in practice, we get some information. We can construct a mass function by comparing our evidence about some variable X to some hypothetical situation in which you would receive a randomly coded message about that variable X. So a mass function M can be elicited by finding the coded message canonical example that is the most similar to our evidence. It's like with probabilities, one way to elicit probabilities is to compare some situation with drawing a ball from an urn. Okay? For example, will it rain tomorrow? You can say, okay, I don't know, I'm not sure, but my feeling of uncertainty is the same as if I drew a ball from an urn that contains, say, 90% of black ball. Okay? So to say that for me, there is 90% chance it will rain tomorrow, it means that it's the same. I mean, I have the same feeling of uncertainty as if I took a ball from an urn and there is, in this ball, there is 90% of black balls. Okay? And I believe that to the degree 90% that I will get a black ball. Okay? So this is a kind of urn canonical example for eliciting probabilities. Here, with belief function, the canonical examples are a little bit more sophisticated. Okay, they are these randomly coded message examples. Okay. Here, the difference is that the probabilities are not about the occurrence of events, but about the meaning of evidence. Okay, here are some useful definitions. So, okay, so I forgot to say here that the sets, this is a very important definition, the sets that have a positive mass are called the focal sets, okay? So if M of A is strictly positive, A is said to be a focal set of A. So a particular case is when you have only one focal set, okay? So you are sure that X belongs to some set A, absolutely sure, okay? So such a mass function is said to be logical, okay, because it's equivalent to a logical proposition X belongs to A. Okay? And we will denote it like this, M sub A into brackets like this. And of course, there is a one-to-one correspondence between logical mass functions and non-empty sets. Okay? In particular, if that focal set is omega, the whole omega, the mass function is said to be vacuous. Okay? We will denote it like this, and it represents total ignorance. Another special case is where the focal sets are singletons. Each focal set has only one element. Okay? Such a mass function is said to be Bayesian, and it is basically equivalent to a probability mass function. Okay? So you see here we can recover a set as an example where all the mass is assigned to only one set, okay? And we can recover a probability when the distribution, where the masses are given to singletons, to sets with only one element. Okay, then next we have the notions of belief and plausibility functions. So given a mass function m on omega, we define corresponding belief and plausibility functions as mappings from the power set of omega to 0, 1, defined as follows. So Bell of A is the sum of the masses M of B for all subsets B of A. Okay, so you sum up the masses given to all subsets B of A. Okay. And this is interpreted as a measure of the total support given by the evidence to set A. Because if we know that the truth is in B and B is included in A, then we know the truth is in A. Okay. Then the next function is called the plausibility function. The plausibility of A is defined as the sum of the masses M of B given to all subsets B whose intersection with A is non-empty. So here and this is interpreted as a measure of, we can say, consistency of the evidence with A, okay? Because if we know that the truth is in B and B intersects A, then this is consistent with the truth being in A, okay? And, okay, B intersection A is non-empty. This is the same as B being not included in the complement of A, okay? So PL of A is also 1 minus Bell of the complement of A. This notation A bar denotes the complement of A. So the degree of plausibility in A is 1 minus the degree of belief in the complement of A. So that's why PL of A can also be seen as a measure of the lack of support given by the evidence to the complement of A. So we can, you see here that we don't have only one set function like in probability theory, the probability measure. Here we have two functions, okay? So the uncertainty about some event, A, is not represented by only one number, but by two numbers, a degree of belief, which tells us how much the evidence supports A, and a degree of plausibility, which tells us to what extent the evidence is consistent with A, without directly supporting A. Okay? And we have this important duality relation between these two measures. So coming back to the Rothian example, so we have this mass function. So here I give the value of Bell and PL for some of the, actually there are 2 to the 5 possible subsets, but I give here the values of Bell and PL for only some subsets. So the empty set has a degree of belief and plausibility 0, okay, because no non-empty subset is included in the empty set, okay, so Bell is 0, and no set has a non-empty intersection with the empty set, so the plausibility is always 0, okay. Then if you take the singleton tree, so the hypothesis that the object is a tree, okay, can we believe that? Does the evidence support that? No, because the evidence only tells us that we have either a tree or an obstacle. The evidence does not directly support tree, so the degree of belief is 0. Is the evidence consistent with the contents of the region being a tree? Yes, because either the sensor is working, it tells us we have a tree or an obstacle, so it can be a tree. or the sensor is not working. We don't know anything, so we can have a tree. Okay, so the evidence is fully consistent. Okay, with there being a tree, and this is translated here into the fact that the plausibility of tree is 1. Okay, you see, because tree obstacle intersection tree is not empty, it's 3. So we take this 0, 9, and omega intersection 3 is 3 also. So we sum up 0, 9 and 0, 1, we get plausibility of 1. The same for an obstacle. Do we have a tree or an obstacle? Okay, does the evidence support that? Yes, it supports that because the sensor tells us we have either a tree or an obstacle. Okay, so the degree of support is the probability that the sensor that tells us that is working. So it is 0, 9. Okay, and it's also fully compatible with the evidence because if the sensor is broken, we still may have a tree or an obstacle. So the plausibility in 1 is 1. Okay. You see here immediately that these two functions are not additive as opposed to a probability because our degree of belief of a tree is 0, for obstacle is 0, but either a tree or an obstacle is 0.9. Okay. And also the plausibility that we have a tree or an obstacle is not the sum of the plausibility of having a tree and the plausibility of having an obstacle. So these two functions are not additive. So you have to forget this about this additivity assumption, okay, when working with belief functions. Okay, so some other examples. Okay, do we have, for example, a tree or the road? Hypothesis, we have a tree or the road, okay? So the evidence that does not directly support that, okay? So because TO is not included in TR, so our degree of belief is 0, but it is fully consistent with the evidence. And do we have a road or the sky? Okay, so here the degree of belief is 0, okay, because none of these two focal sets is included in that. And the degree of plausibility is 0.1, okay, because here T or O, TO intersection RS is empty, so we don't count this. And omega intersection RS is not empty, so we take only the 0, 1. So the evidence is, say, mildly consistent with the hypothesis that we have either a road or the sky. Okay, it can be possible only if the sensor was not working. And for omega, we have 1 and 1, and this is always the case. Okay, the belief and the plausibility of the whole set omega are always equal to 1. Okay, so here these are some elementary properties. So as I said, Bell of empty set is always equal to PL of empty set, it is 0. Bell of omega is equal to PL of omega, it is 1. Then the Bell function is superadditive, meaning that Bell of A union B is always larger than Bell of A plus Bell of B minus Bell of A intersection B. So with a probability measure, you would have an equal sign. So you see here the constraint is weaker. Okay, we somehow relax constraint of probability theory. The plausibility measure is subadditive. Okay, here we have these inequalities. But if M is Bayesian, remember Bayesian means that the focal sets are singletons. So basically, this is probabilistic information. In that case, the Bell and PL functions are equal, and they are a probability measure. So we recover, okay, the notion of probability measure in the special case where the evidence points to precise hypothesis. Okay. Okay, formally, it can be shown that a set function, assume that, okay, first it can be shown that a belief function, okay, is completely monotone. It means that it verifies these inequalities. So this is a generalization of this one. Okay, actually it works for any collection of K subsets. You take a collection of K subsets of omega, and these inequalities, okay, give you a bound for the degree of belief of the union of the AI. Okay, and it can be shown also that if you start with some set function, it is a belief function, okay, for some mass function M, if and only if these inequalities are verified. Okay, so I give you a set function. You can verify if it is a belief function. Okay, it is a belief function if and only if all these inequalities are verified. Okay, so I will not, of course, prove this. We don't have time, but okay, this is an important theorem because it gives us a characterization of what is a belief function. Okay. A set function qualifies as a belief function if and only if it verifies all these inequalities for any k. Okay, and then we can recover the mass function from the belief function by these equalities. Okay, so if I give you the belief function, you can recover the underlying, say, mass function, okay, by these qualities. Okay, so finally now we have, up to that point, we have defined three functions: a mass function, a belief function, a plausibility function, and there are formulas to transform one function into another one. Okay, for example, this is a relation between Bell and PL. This is how to get M from Bell, M from PL. I showed before Bell from M and PL from M. So basically, these three functions are three equivalent representations of some evidence. Okay, if you get any one of these three functions, you can recover the other two. Okay? So depending on what you are, which operation you want to perform, it might be more convenient to use one form or the other. Okay, and we'll see later still yet other functions which are also equivalent representations. Okay, now a special case is that where the focal sets of M are nested. Okay, you have, for example, R here focal sets, A1 to AR, and they're ordered by inclusion, okay, like Russian dolls, okay. Then the mass function is said to be consonant. In that case, it is not difficult to show that for any two subsets A and B of omega, the plausibility of A union B is the maximum of the plausibility of A and the plausibility of B. And this is actually the definition of a possibility measure. So we get something called a possibility measure, which is studied in a whole approach called possibility theory as a special case where the focal sets of the mass function are consonant. And actually the belief function is then called the necessity or certainty measure. And also we can recover the plausibility of any subset A as a maximum of the plausibility of the elements of A. Okay, the plausibility of a subset is the maximum of the plausibility of its elements. Okay. Here I didn't mention this notation, PL with a lowercase p. I call it the contour function, and it is a function that gives the plausibility of each single element of omega. So in that sense, we can say that the theory of belief functions is somehow more expressive than possibility theory because we recover a possibility measure as a special case. Okay, but we should here notice that these two theories are distinct because they have different mechanisms for combining information. Okay, and we'll see shortly how we combine information in Dempster-Shafer theory. Also, we say that a probability measure P on omega is compatible with M if it verifies these inequalities, okay, meaning that the probability of any event A is bounded by the belief in A and the plausibility in A. Remember that the Bell of A and PL of A form an interval, okay? So if the probability of A is always comprised between these two bounds, we say that the probability measure is compatible with the belief function. So we can define the set P of M of all probability measures compatible with M. This is called the cradle set of M. So a belief function defines a whole family of probability measures which are compatible with it. And we also have that the belief function is the lower envelope of that family of probability measures, meaning that for any event A, Bell of A is the minimum of P of A for all compatible probability measures P. Okay, but here we have to be careful that if you start with a set of probability measures and you take the lower envelope, it is not always a belief function. So a belief function defines some kind of sets of probabilities. Okay, but in general, okay, you have other theoretical approaches that work with sets of probability measures. Okay, and this approach is distinct from belief functions. Okay, because actually a set of probability measure, if you take you start with any set of probability measure, you take the lower envelope. Sometimes it's a belief function, sometimes not. So in some sense, we can say that here the notion of set of probability measure is more general than belief function. But again, this theory of imprecise probabilities is distinct from the theory of belief functions because they have different mechanisms for combining information. Here again, it is a dynamic aspect of the theory, how you accumulate, you update information. This is distinct, okay, in the theory of imprecise probabilities and in the theory of belief functions. Okay, so now how to combine information? This is in this approach we have an operator called Dempster's rule of combination. Okay, and this is very important. This is really the cornerstone. Or there are two cornerstones. There are two basic notions: belief functions on the one hand, and Dempster's rule for combining information on the other hand. Okay. So I will come back to my road scene example. And so remember that, okay, you remember that we had this first piece of information, the LiDAR sensor evidence gave us a mass function. Now I call it M1. And assume that we have now another sensor, let's say a camera, that returns another mass function, M2. Okay, this camera sensor, for example, we see the color is green. So this can be either the grass or a tree. Okay, and so, but also this evidence is always 80% reliable. So we assign a mass 0.8 to grass or tree and 0.2 to omega. How to combine these two pieces of evidence? So here we have this view. Here we have S1 is the set of states of sensor number 1. S2 is the set of states of the second sensor. You see here the second sensor is working, tells us that we have a tree, grass. If it's broken, it doesn't tell us anything. So now assume that we know that both sensors are working. So if both sensors are working, the first one tells us that we have an obstacle or a tree. The second tells us we have a tree or grass. So what can we deduce? We have a tree, right? We just take the intersection. What is the probability that both sensors are working? Okay, so here we need an assumption of independence. If the two sensors fail independently, the probability that they are both working is a product of the probability. So you see, we can take here each pair of interpretations, seeing the elements here of S1 and S2 as interpretations of the evidence. We can take both pairs and we can assign to each pair the intersection of the images, okay, by gamma 1 and gamma 2. And to each pair, when we take on the product space S1 cross S2, we consider the product measure. Just compute the product of probabilities. Okay. So here we can do the calculation like this. Okay. So for example, if sensor 1 is not working, okay, it doesn't tell us anything, but sensor 2 is working. It tells us we have a tree or grass. So we know that we have a tree or grass, okay? And the probability is 0.1 times 0.8, which is 0.08. Okay, so we have these four possibilities, and that gives us this combined mass function. Okay, now we have a little bit more complicated case where the evidence is conflicting. Because sensor 1 tells us we have an obstacle or a tree, and sensor 2 tells us we have the road or grass. Okay. So if both sensors are working, what do we have? A contradiction. Okay, because here the intersection is empty. So what can we deduce? We can deduce that it is impossible that both sensors are working. Okay. So we can eliminate, and there are initially four possibilities: broken, working, broken, broken, working, 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 broken. Okay. Now we can eliminate one of these four possibilities. Okay, because it leads to a contradiction. The intersection of the images is empty. So now, because and we don't want to assign any mass to the empty set, so we will consider the product measure on S1 cross S2, and we will condition this product measure on the set of pairs of interpretation which is consistent, meaning whose images are not disjoint. Okay. So here we do this here. So we have these four possibilities, but this one gives us the empty set. Okay. So we want the mass here to be 0. Okay. So conditioning here, it amounts to putting a 0 here on the empty set and renormalizing, okay, the other masses so that the sum remains equal to 1. Okay. So for example, the mass on obstacle or tree is 0.9 times 0.2, but divided by 1 minus 0.78, which is 0.28. We have to renormalize, okay, everything after we have forced the mass on the empty set to be 0. And this is actually some conditioning operation, okay, on the product measure, product probability measure. Okay, so this is now the formal definition of Dempster's rule. Okay, so first, given two mass functions M1 and M2 on the same frame, we define the degree of conflict, which I denote here by the Greek letter kappa, as the sum of M1 of B times M2 of C for all focal sets B and C whose intersection is empty. Okay, so this is a measure of the extent to which the two pieces of evidence are conflicting, the degree of conflict. So if the degree of conflict is equal to 1, then the two items of evidence are completely contradictory, so they cannot be combined that way. Okay? But if the degree of conflict is less than 1, we define their orthogonal sum like this. Okay, it's a new mass function which I denote like this symbol. So to compute the mass assigned to A, we take here each focal set B of M1 and each focal set C of M2, whose intersection is A, and we multiply the masses. Okay, so we do this for each pair B and C whose intersection is A, and then we renormalize by dividing by 1 minus the degree of conflict. So this is really the basic operation for combining evidence in Dempster-Shafer theory. So the approach is that we have some evidence, we represent each piece of evidence by a mass function, and then we combine the total evidence using that operation. Okay, this operator has nice properties. It is commutative, and combining M1 with M2 is the same as starting with M2 and combining with M1. And it is associative. So if you have three mass functions, you can either combine M2 and M3 and combine the result with M1, or start with combining M1 with M2 and combining the result with M3. It is the same. So you can drop the parentheses. Okay. Also, a mass function M is not changed if it is combined with a vacuous mass function, okay, which I denoted before M sub question mark here, I change notation. And so that vacuous mass function is a neutral element, okay, for that rule, for that operator. And it makes sense because if you have two sources of information and one doesn't tell you anything, it doesn't change what the first one tells you. Okay, so. And then we have this very important property, which I ask you to remember because I will use it later today and also tomorrow, and maybe it will be used also later in other lectures. So assume that you call PL1, PL2, the contour functions corresponding to M1, M2. Remember, the contour function is a function that gives the plausibility of any element, any single element, okay? And you call PL1, 2, the contour function corresponding to M1 combined with M2. So you can combine PL1, 2 to compute the combined contour function. You don't need to compute the mass function. You can just multiply PL1 with PL2, term by term, and divide the result by 1 minus the degree of conflict. So this is much simpler because you see to do this, you just have the order of number of operations is just proportional to the cardinality of omega, instead of being exponential like the cardinality of the set of all subsets of omega. So it is much faster to compute. If you're only interested at the end, all you want to know is the plausibility of each single element. You don't need to combine the mass functions. You can just multiply the contour functions. And if you're only interested not in the precise value of the probabilities, but you only want to know which is the element of omega with the largest plausibility. You want to find the maximum plausibility hypothesis, then you don't even need to compute that degree of conflict, okay? And this becomes, that case, very, very fast. And this is what we will do in some applications I will tell you about later today and also tomorrow. Okay, here this is a slide about some misconception about Dempster's rule, okay? If you read, actually, I would say even unfortunately, in 1979, Zadeh published a report about that new Dempster-Shafer theory that he just read about in Shafer's book. And he concluded from some example that Dempster's rule yields counterintuitive results. And then this has been repeated, and still now it is still being repeated in many papers. You can still see many times that Dempster's rule yields counterintuitive results, okay? And usually the next step is to introduce yet another rule, which is supposed to overcome this weakness of Dempster's rule, which is not intuitive. But if something is not intuitive for you, it may be just that you didn't understand, okay? You don't understand, so your intuition maybe is wrong. And I would argue here that this is the case. What was Zadeh's example? Zadeh's example take a case where, okay, I don't remember maybe it was 3 diseases, for example. Assume you have 3 diseases, A, B, and C, and 2 medical doctors, okay? And the first one gives you a mass function like this, okay, with a mass 0.99 of A on A, 0.01 on B, and 0 on C. It means that expert 1 considers that C is impossible, absolutely impossible, because the mass is 0. Okay, this is very important in the story. Expert 1 tells you that C is impossible, and A is much more supported or likely than B. Okay, expert 2 tells you that A is absolutely impossible, okay? And expert 2 believes that C is much more supported by the evidence than B. So if you combine these 2 mass functions by Dempster's rule, what do you get? You get a logical mass function with focal set B, okay, meaning now you're sure that B is true. And then they say this is counterintuitive because expert 1 believes that it's A, expert 2 believes it is C, and we conclude B. Okay? So it seems, if told like this, the story is not strange, okay? But if you say expert 1 tells you that C is impossible, expert 2 tells you that A is impossible, then it can be only B, it can be only B. Then it makes a lot of sense. Okay, there is nothing wrong with that. So actually, what I would argue, and I think my colleagues here will argue the same, is that actually Dempster's rule does produce sound results when used and interpreted correctly. Okay, so you know that in probability theory we have an operation called conditioning, and yeah, so maybe I should have put it. Okay, so in probability theory, we have an operation conditioning. Okay, you take a probability measure, you condition it on some event, okay, and you get a conditional probability measure. So it's like combining a probability measure with a set. Okay, you actually combine two things, but they are not symmetric. You combine a probability measure with a set. You have a combined probability, a conditional probability measure. Actually, here in Dempster-Shafer theory, conditioning is a special case of Dempster's rule, okay? Where you take some mass function m and you combine it with a logical mass function m sub a with focal set a, and you can denote the result like this. You can say the result is the mass function m conditioned on a. And it can be shown that it's simple calculation. The plausibility of b given a, with this definition, is the plausibility of a intersection b divided by PL of a. You recognize here formally the same operations as for computing conditional probabilities, okay? It means that when the mass function m that you condition is Bayesian, what you get, the resulting conditional belief function, is actually remember, if m is Bayesian, function Bell or PL or probability is a probability measure. So you get exactly the same result as by conditioning that probability measure using the rule of probabilities. So we can say that Dempster's rule is really a generalization of Bayesian conditioning. Okay? If you have a Bayesian mass function that gives you actually a probability, you combine it by Dempster's rule with a logical mass function, you get the conditional probability. So the probabilistic conditioning is really a special case of Dempster's rule. Okay, finally, I quickly mentioned that as we have seen the belief function, the plausibility function, there's yet another function called the commonality function, which is defined by these qualities. So Q of A is the sum of M of B for all the sets B that include A. So you see here this symbol is in the other direction as compared to the belief function. You sum up the masses given to all supersets of A. So it can be shown that M can be recovered from Q by these equalities. So this is yet another equivalent representation of the belief function. What is its interpretation? It's not very easy to really find an interpretation of this, but it has a remarkable property with respect to Dempster's rule. If Q1 and Q2 are commonality functions associated to M1 and M2, then Q12, the commonality function associated to the orthogonal sum of M1 and M2, can be computed like this by just multiplying Q1 and Q2 pointwise, okay? So this is of course, much simpler than taking all the intersections of the focals, at least conceptually. So this commonality function is very useful for that, okay? Because it has this remarkable property with respect to Dempster's rule. It is very easy in the space of Q commonalities. It is very easy to combine information. You just combine the commonalities pointwise. Okay, so there is another rule that looks a little bit like Dempster's rule. It is, I call it Smet's disjunctive rule, and it's defined like this. So we have, as before, assume that we have these two, this two randomly coded messages. Okay, they are also defined random sets. I will come back later, the last day, I think, to this idea of random sets. So you have two coded message, okay? And so previously we assumed that both messages were reliable, okay? It means if you know the true meaning of the message, okay, you get some proposition which is true. Okay? Here we relax this assumption. We assume that at least one of the two messages is true. Either one or the other is true. So now when you receive the two messages, you will take the union. Okay. So you assume that if the true codes are C1 for the first message and C2 for the other message, you conclude that X belongs to gamma 1 of C1 union gamma 2 of C2. You see? So instead of the intersection in Dempster's rule, you use the union. And this is, and you get now this expression. This is another way to combine two mass functions. Okay. Here we say that it is a disjunctive combination. Okay. It's like it generalizes the union of sets. Dempster's rule generalizes the intersection of sets. This rule generalizes the union. And here you don't need to renormalize because you never get the empty set by taking the union of non-empty sets. Okay, so you don't have conflict. And you have this. Intuitively, you see there is some kind of duality between this disjunctive combination and Dempster's rule. Okay, and here we can show that the belief function corresponding to M1 combined disjunctive with an M2 is a product of the belief functions of M1 and the belief functions of M2. Okay? So you have similar equality here that you had with commonalities for Dempster's rule. Now here you have it for belief functions. So this operation is just taking the two belief functions, multiplying them pointwise. You get a new belief function. This new belief function is less precise, less specific. Like you take the union of two sets, you get a set which is larger. Okay, so you can easily imagine that if you combine a lot of information like this, every time it's less precise. So it's like you have kind of dilution of information. Okay, the more using this rule, the more you combine information, the less you know in one sense, because the more imprecise is your mass function. Okay, so this is the first part. I have only half an hour left, which is not much. Okay, yeah. Okay, so with that, with what I presented till now, you have, let's say, really the basics, but it is enough in many applications. Actually, maybe 90%, maybe more of the papers on belief functions use only what I've presented till now. Okay. But actually, for more advanced application, actually many applications, you need more. You need more than that. So I will first introduce the notion of informational comparison of belief functions. So the question we ask is the following. Assume that we have two mass functions M1 and M2 defined on the same frame of discernment omega. In what sense can we say that M1 is more informative than M2? For example, you have two sensors. Okay, well, from one sensor you get a mass function M1, for the other sensor you get M2. In what sense can you say that sensor 1 is more informative than M2? So consider a special case where the two mass functions are logical with focal sets A and B. So sensor 1 tells you truth is in A, sensor 2 tells you the truth is in B. So if A is included in B, you can surely say that sensor 1 is gives you more precise information. Okay? So here we'll say that M sub A is more informative or more committed than MB if and only if A is intersection is included in B. So how can we now extend this idea to arbitrary mass functions? So there is one definition here. We can say that M1 is more PL more committed than M2, or more committed in the sense of plausibilities, and we denote it like this. If for any subset A of omega, PL1 of A is less or than or equal to PL2 of A. So the plausibilities computed from M1 are smaller than the plausibilities computed from M2. Or equivalently, and this is equivalent to saying that for any subset A, the degree of belief in A obtained from M1 is always larger than or equal to the degree of belief from M2. So if any event, say A, is more supported considering M1 than considering M2, we can say that M1 is more committed, okay, or more informative than M2. And this ordering has in particular some interpretation in relation with the cradle sets. Remember, the cradle set of a mass function is the set of all probability measures that are compatible with it. So in terms of cradle set, this translates to this inequality translates with the inclusion of cradle sets. Okay? So M1 is more committed than M2 according to plausibilities if and only if the cradle set of M1 is included in the cradle set of M2. Okay? So if in applications where you see mass functions as defining sets of probabilities, this makes a lot of sense. Okay? The set of probabilities corresponding to M1 is included in the set of probabilities corresponding to M2. So you have these properties. Okay, first it extends set inclusion. So this is really an extension. If you have two logical mass functions, M sub A and M sub B, MA is less informative in that sense than MB, if and only if A is included is subset. A is a subset of B. And this operation has a greatest element, which is a vacuous mass function. Okay? Meaning the vacuous mass function is less informative, less committed than any other mass function. Makes sense because it represents A. Okay? So this is a meaningful notion of ordering of mass functions with respect to their information content. You could also use a commonality function to define an ordering. And the rationale is this, that assume that M1 is a combination of M2 with some mass function M. And assume there is no conflict between M and M2. Then Q1 of A, for any A, Q1 of A is a product of Q of A, and Q is a commonality function corresponding to M, times Q2 of A, and this is less than Q2 of A. And certainly in that set, we can say that M1 is more informative than M2 because M1 is obtained by combining M2 with something conjunctively. Okay? So using that reasoning, we can propose another definition. We can say that M1 is Q more committed than M2, and we denote it like this, if and only if Q1 of A is less than Q2 of A for any A. So once again here, the rationale is that M1 can be seen as a combination of M2 with some function, mass function M, which has no conflict with M2. Okay. Okay, this ordering also extends set inclusion, and it also has a greatest element, which is the vacuous mass function. Okay, so it seems that it's equally reasonable as the previous one. Now we have a third definition, okay, which is called specialization. We say that M1 is a specialization of M2, and we denote it like that, if M1 can be obtained from M2 by distributing each mass M2 of B to subsets of B. So here, it means you can write M1 like this, okay? So here S of AB, it is a proportion of M2 of B transferred to A. So you start from M2, you take each mass and you distribute it in some way to subsets. So it means the mass flows from some focal sets to more precise focal sets, smaller focal sets. Okay, so this is makes sense also to consider that in that case, M1 is more informative, more committed than M2. And this relation also extends set inclusion. The vacuous mass function is also a greatest element. And this notion is stronger than the previous two, so meaning that if M1 is a specialization of M2, then M1 is more committed than M2, according to the two previous definitions I presented before. So it is a stronger notion of inclusion. Okay, so now what can we do with that? Okay, we can apply something called the least commitment principle. It plays the same role as the maximum entropy principle in probability theory. When we're working with probabilities, sometimes we have some unknown probability distribution. We define some constraints, okay? And then we search for the probability distribution with maximum entropy that verifies this constraint. It's a principle of maximum uncertainty. You want to say something, but just not more than what you know, okay? So here we can use some kind of similar principle here with belief functions. We say that when several belief functions are compatible with some constraints, the least informative, according to some ordering, but I gave you 3 orderings, okay? So depending on the case, we can use one or the other. The least informative should be selected. It's a kind of principle of conservatism, or you see, you want to formalize some knowledge in terms of a belief function, okay? You want to give the belief function, which is as little informative as possible while verifying the constraints. Okay? You don't want to say more than what you know. This is the idea. And so this is a very powerful method for constructing belief functions. And here I plan to tell you about a rule, which I call the cautious rule. It is an operation to combine dependent information. Okay, we have seen that Dempster's rule has the idea of combining independent pieces of information. The cautious rule is another rule that is designed to combine information that may be dependent. Okay, and it's derived from the principle of minimal commitment. Okay, but actually I learned that Frédéric will tell us about this afternoon, so I can skip this part and let Frédéric present it this afternoon, and I will skip directly to the last part. So this is good because I was a little bit late, so now I can. Okay. And I will speak now of a very important, I can skip the cautious rule because it's just some separate topic, but I cannot skip compatible this part because it's really fundamental. And in particular, Prakash will need this later in the next talk, okay? So I come back to the road scene example. Okay, remember that the set omega is this. Assume that now that we have a vegetation detector. Okay, it's a kind of software sensor that detects vegetation. So this detector can only determine if a region of the image contains vegetation or not. So for this detector, the frame of discernment, call it theta, has only 2 elements. Either we have vegetation or not. But we have a correspondence, okay, between the elements of theta and the elements of omega, okay, because grass and tree are vegetation, okay. So when this sensor tells us we have vegetation, it means that we have either grass or tree, and not vegetation corresponds to road, obstacle, or the sky. So you can see that the elements of omega can be obtained by splitting some of the elements of theta into finer possibilities. Okay, vegetation can be either grass or tree. Not vegetation can be either road, obstacle, or sky. We say that omega is a refinement of theta, And conversely, theta is a coarsening of omega. So this is a general definition. We have some set theta, two sets, theta and omega. We say that omega is a refinement of theta if there is a mapping, denoted here by rho, from subset of theta to subsets of omega, which is such that the image of each singleton of theta is a subset of omega, and the images of all these elements form the partition of omega. So we can say that we obtain subsets in omega by splitting here elements of theta into finer possibilities. Okay? So you see here, this is a definition. So the set of images of singletons in theta forms the partition of omega. It means they are pairwise disjoint, and the union is omega, like you see here. This is image of omega of theta 1, the image of theta 2, the image of theta 3. These three parts are pairwise disjoint, and their union is omega. Okay? And then we define that the image of, let's say, theta 1, theta 2 is the union of the images of theta 1 and theta 2. So if there exists such a mapping, we say that omega is a refinement of theta. Okay? And conversely, theta is a coarsening of omega. So this is a very important idea, okay? Because you see, when you use probabilities, for example, you need to define the universe of discourse. And a very important idea is that there is no absolute universe of discourse. You can always take a possibility and split it into finer possibilities, okay? And you can do this indefinitely, okay? So in many applications, we need to let the degree of refinement, okay, of the universe of discourse, we have to let it vary. And this is the topic I want to tell you about here in this part. So in the routine example, assume that the vegetation detector provides the following mass function on theta. Okay, there is some mass on vegetation, some mass on not vegetation, and some mass on don't know. How to express the same information in omega? So here with a mass function on theta, we want to express it in a refinement of theta. So this is quite easy. We just take each mass given on to a subset of theta, and we can transfer this mass to its image by the refining application rho. Okay, it means that if we put 0.6 on V, but V in omega means grass or tree, so we put the mass 0.6 on the set grass or tree. Okay, because grass or tree is the same thing as vegetation. Okay? Similarly, the mass on not vegetation will be transferred to the image of not vegetation, which is road, obstacle, and sky. The mass on theta will be transferred to omega. And finally, we get that following mass function on omega. We denote it like this with an up arrow, and we call it a vacuous extension of m theta in omega. So in that case, you see, this is very easy because it's like omega gives you a more richer language. Okay? So if you can say something in some language which is quite poor, you can always say the same thing in a richer language. Okay? For example, if I know only 200 words of Japanese, for example, which I don't even know actually, but I have beginner in Japanese, for example. If I can express some idea with that 200 words, I can express the same idea with a full Japanese language. Okay? So, and I don't lose any information. Okay? So this is the first idea, the idea of vacuous extension. Let us know that we have the opposite problem where we express some information in omega. So we start with a mass function on omega, which is given here. Now the question is how to express it in theta. So now we go from a finer frame to a coarser frame. It's like now you have some sentence in Japanese, using the full Japanese language, and You want to explain it to me, and I know only 200 words. Okay, so you have to approximate it. I probably will not be able to express the same ideas exactly, but you will try to find some approximation that I can understand with my 200 words. Okay, so this is a little bit the same idea. You can already see that we are going to lose information in the process. And indeed, this cannot be done without loss of information because, for instance, okay, you have some mass on 3, but in theta, there is nothing that means exactly 3. We have only vegetation or not vegetation. Okay? So maybe 3 can be approximated by vegetation, okay? But it's not the same meaning. Lose information. We knew it was 3, not grass. Now it's only represented by vegetation. We have lost information. So here, assume that you start with some subset B of omega. In general, there will not be a subset of theta whose image is exactly B. So that mapping rho does not have an inverse. This is a problem. Okay? But we can still find 2 mappings. We can, for each B, we can define the set of theta whose image is included in B. Okay? And this is the definition. We call this the inner reduction of B. It's some kind of approximation, an inner approximation of B in theta. You take the set of small theta whose image is included in B. Another useful definition is that of the outer reduction of B, which is a set of theta whose image has a non-empty intersection with B. So in my example here, you see in this case, the inner reduction of B is empty, okay? But because there is no small theta whose image by rho is included in B, but the outer approximation of B is theta 2, theta 3, because you see that theta 2, rho of theta 2 intersection B is not empty, and the image of theta 3 intersection B is not empty. So in the previous example, so we had 3 focal sets in omega, tree orb, circle, row of sky. For these 3 sets, the inner reduction is empty. From that, we can already see that this definition of tree is not very useful, because many times you just get the empty set. Okay? The other definition is more useful, actually. And here for tree, so tree in theta, the outer approximation or outer reduction is vegetation. Okay, it's like the best way I can find some close meaning in theta. Okay, tree or obstacle becomes vegetation or not vegetation. So here you lose all the information. Okay, because tree is vegetation, obstacle is not vegetation. So expressed in theta, it just tells if you know you have either tree or obstacle. In theta, it's just is vegetation or not vegetation. So you have lost information. And for road or sky, both are not vegetation, so the outer reduction in theta is not vegetation. So this is a way to approximate, like to convey the meaning of B in theta, okay, but you can only do it in an approximate way. Actually, it's in a conservative way. So now, if you have some mass function on theta, you define its restriction. You start with the mass function on omega. You define its restriction in theta by transferring each mass, m of B, to the outer reduction of B. So you take each mass f m of B, and it is given to the outer reduction of B. Okay? So that for any A here in theta, there may be several B in omega with outer reduction in A. So you have to sum up these masses. So for instance here, and you know this operation by a down arrow. And so here, starting from the previous mass function in omega, we get this. If you take this restriction and you compute its vacuous extension in omega, so they say you go from omega to theta and then back to omega, you don't get the same thing as you started with, okay? Because now you get this mass function by compare it to the previous one here. This one is less informative. Okay, the focal sets are bigger because now you have lost information. So if you go from omega to theta and back, you have lost information. Okay, now this is a new definition. Given two frames, theta 1 and theta 2, we say that they are compatible if they have a common refinement. Okay? So, for example, here we have seen that theta 1 containing vegetation or not vegetation is omega is a refinement of theta 1. Now, assuming that theta 2, which is either the ground or not the ground. Okay. This is also a coarsening of omega, and because the ground means the grass or the road, and not the ground means a tree, obstacle, or sky. Okay, so these two frames, theta 1 and theta 2, both have omega as a refinement. We say that they are compatible. So now if we have two mass functions defined on two compatible frames with common refinement omega, we can combine them by Dempster's rule. We just compute the vacuous extensions in the common refinement omega. And we have seen how to combine two mass functions defined on the same frame. Okay. If we have evidence expressed in compatible frames, we can express this evidence in the same frame, okay, which will be a common refinement. And so we have this notation. And so the vacuous extension is implicit here in this notation. And Prakash will show us smart ways to do this kind of operations when you have a lot of variables and mass functions. Okay, so here this is a small example. So I start with a mass function on theta 1 and a mass function on theta 2. I compute their vacuous extensions. Okay, as I explained, we just transfer, for example, the mass on ground is transferred to grass or road. The mass on not ground is transferred to tree, obstacle, or sky. Okay, and then now I have two mass functions on the same frame, and I can use Dempster's rule. Okay, and here there's no conflict. Okay, so here you have masses assigned to each focal set. Okay. Okay, so now I will give you an example of an application of this, and you will have an idea of how powerful it is to combine information. This is an example in object association. Assume that you have two sets of objects perceived by two sensors. I call them E and F. For example, here you have sensor 1 perceives 4 objects, F1, F2, F3, F4. The second sensor perceives 3 objects, E1, E2, E3. We want to match these two sets. So, for example, here we might conjecture that E2 corresponds to F1. Okay? And E3 might correspond to F2, and E1 might correspond maybe to F4. F3 doesn't have any correspondence in the second set. So we want to find a way to match these two sets. Okay, so these two sets may be perceived by two sensors or by one sensor at different times. And this can be, the second case, it can be used for tracking. Okay. So for this, we need information. We will see how to use information, for example, from the position of the objects. Here I reason only with the position, the location of the objects. But sometimes we can use other information like the velocity, speed, okay, the class, okay, and so on. Right? So for each pair of objects, we take one object in first set, capital E, one object in the other set. We will use information to build a pairwise, what I call a pairwise mass function on the frame, which I denote by theta ij. So theta ij has two elements. Hij means that the objects EI and Fj are the same object. Okay, they should be matched. For example, here I consider F1 and E2. Okay, either they are the same, object or they are different objects. There are only two possibilities, okay? So I will compute mass functions like this, okay, for each pair of an object in E and an object in F. So if there are n objects and p objects in the two sets, there will be n times p such pairwise mass functions. And then I will find the matching relation with the highest plausibility. So here we'll use Dempster's rule. Okay, so now we reason with two objects, okay? How can we reasonably use a position? Assume we know the position, so we have some estimate of the position of these two objects. But we can compute the distance. Okay, let dij be the distance between the estimated positions of the two objects. So if the distance is small, this supports the hypothesis that they are the same. If the distance is large, this supports the assumption that they are not the same. Okay? And so we can define a mass function like this that will assign some mass to hij. The two objects are the same. The mass will be defined as a function, some function of the distance. Okay? So this function phi should be decreasing, because the larger the distance, the less likely it is that the two objects are the same. Okay? Then we will have some mass on hij bar. The objects are not the same. Okay? And some mass on theta. Here I have another parameter alpha, which characterizes the degree of confidence in the sensor. Okay? You see, if we have confidence 0, okay, then we get all the mass on theta ij, which is vacuous. Okay? If the confidence is 1, then you don't have a mass on theta. Okay, you only on hij bar. So here, depending on the application, we can postulate some form for the function phi and let it depend on some parameters that we can fit and so on. Okay, but this is the basic idea. So we start seeing here how we use that mass function formalism to represent evidence. Okay, so here this is the evidence from the distance between the positions of the two objects. Okay? The larger this distance, the more we believe that the objects are different. The smaller the distance, the more we believe they are the same. Now, using velocity information. So assume we can measure the velocity vectors of the two objects. Okay? Let dij prime the distance between these velocity vectors. So here, if this distance, if the velocity vectors are very similar, very dissimilar, okay, one is going this direction, one is going this direction, so probably it's not the same object. But if the velocities are similar, the two objects move with the same speed and the same direction, it doesn't mean that they are the same. For example, in a highway, you have different cars, they all go in the same direction and roughly the same speed, and there are different cars. So here, a large value of dij prime is evidence for hij bar, but a small value of dij prime is not evidence for hij. So here, by looking at the velocities, you can only have evidence that can point to hij bar. But once again, two objects that move in different directions truly are not the same, but two different objects can very well move in the same direction. So here we'll define a mass function like this, where we assign some mass to hij bar, which will be some function psi, and that will be an increasing function psi of the distance between the velocity vectors. The larger the distance between the velocities, the more evidence we have that the objects are not the same, and the complement to 1 will be given to theta ij. Here, alpha prime is again some degree of confidence in the sensor information. Now you can sometimes assume that objects belong to classes. For example, there are objects on the road, and they can be trucks, cars, bicycles, motorcycles, and so on. So let omega be the set of possible classes: car, truck, bus, bicycle, and so on. Let Mi, Mj denote mass functions representing evidence about the class membership of the objects. So if two objects do not belong to the same class, they cannot be the same. If you have a truck and a car, believe this is a truck, and you believe this object is a car, then you cannot, this is evidence that they are different. Okay? But if the class is the same, once again, it's not evidence that the objects are the same. You can have two different trucks or two different cars. Okay? So here again, we'll have a mass function that with two focal sets, hij bar, okay, and theta ij. And it can be shown, I don't have time to show it here, it can be shown that the mass assigned to hij bar must be the degree of conflict between Mi and Mj. And we'll come back, we'll do something similar tomorrow in the lecture on clustering. We'll do something tomorrow, okay? So you have some evidence about the class of object EI, some evidence about the class of object Fj. Where if the degree of conflict between these two mass functions is high, it means that you believe they do not belong to the same class. Okay, and then this is transferred. This mass should be transferred to hij bar. So now you have these three sources of information: position, velocity, and class. You can combine for each pair of objects. Until now, we consider only separately each pair of objects. You can combine the three mass functions by Dempster's rule. Now we have NP combined mass function, M superscript theta ij. How to combine them? Okay. Does there exist a common refinement of the frame theta ij? So are the frames theta ij compatible? And indeed they are. So here the underlying frame is the set, I denoted here by curly R, the set of all matching relations. Okay, so here the frame is a set of all matching relations. All the ways to match one object in the first set with an object in the second set, with the constraint that one object in each set can be matched with at most one object in the other set. So I call this set R the set of all admissible matching relations. I denote by R, curly Rij, the subset of relations such that object EI is matched with object Fj. Okay? So this is only a subset of all matching relations in which objects I and J are matched. So to say that object I and J are the same, it is the same thing as to say that the matching relation is such that these two objects are matched. So here Hij, hypothesis Hij corresponds to the subset Rij, to a set of matching relations. Okay? So that R is a refinement of theta ij. So we can take our mass function on theta ij, defined as explained before, and compute its vacuous extension in R. So here we manipulate mass functions in the set of all relations between the two sets, all admissible matching relations. Okay. Here, remark is that that set can be very, very large. Okay. So you will read in some papers that Dempster-Shafer theory belief function is fine, but it cannot be used in very large, very complex problems because the complexity of Dempster's rule is exponential, blah, blah, blah. But actually here, this is an example of an application of belief function in a very large set. Okay? And tomorrow we'll see an application with clustering in even larger sets. Okay, and we can very well apply these ideas of belief function in such sets. So here I compute the vacuous extension. It's very, very simple. Now the mass on Rij is the mass that was assigned to Hij. Here I denote it by alpha ij. The mass on Rij bar is the mass that was assigned to Hij bar. And the mass on the whole set, curly R, is the mass that was assigned to theta ij. Okay. So now we have this n times p mass functions. We can combine them, at least conceptually, by Dempster's rule. Okay. But computing this combined mass function can be very costly, okay, because that set is very good, very big. But actually, if we only want to find the most plausible matching relation, we don't need to compute that whole mass function. We can use this property I mentioned before, that the combined contour function, if you're only interested in the plausibility, okay, of the elements, you can just multiply the contour functions. So, and here, if we want to, we're not interested in knowing the plausibility of each matching relation, but only finding the most plausible one, we don't even need to compute the proportionality constant, and we can just multiply these plausibilities, okay, and we'll get the plausibility up to some constant, okay, and then we can find the most plausible matching relation. So here we have this combined, these pairwise mass functions extended to R. What is the plausibility? If you take some matching relation R here, what is its plausibility? Okay, so if it belongs to Rij, if it means in relation R, objects I and J are matched, the plausibility is the sum of alpha ij plus the mass on R, so that is 1 minus beta ij. Maybe I can take this. R, here Rij, R, if R is here, okay, to compute the plausibility, you sum the masses for all the subsets that contain R, so that is Rij plus R. Okay, so you get alpha ij plus 1 minus alpha ij minus beta ij, which is 1 minus beta ij. Now, if you take R on the other side, okay, now the plausibility of R is the sum of the mass assigned to Rij bar plus the mass assigned to R, and this is 1 minus alpha ij. So finally, you can write it as compactly like this. It's 1 minus beta ij to the Rij, where Rij equals 1 if Ei and Fj are matched in this relation, times 1 minus alpha ij to the 1 minus Rij. And now, so the combined mass function is obtained up to some proportionality constant by multiplying these contour functions. So now you can get the plausibility of any matching relation by this expression. Here the product is over all the pairs of objects. Okay, you can take the log and rearrange the terms, and you see that this is a linear. This function is linear in the Rij. And so maximizing, so the constraints can also, yeah. Okay, so the most plausible relation can be found by solving what is actually a binary linear optimization problem, maximizing this log plausibility subject to these constraints. So these constraints express that each object I can be matched in the first set, can be matched with at most one object in the other set, and conversely, an object in F can be matched with at most one object in E. So these are also linear constraints. So you need to maximize the linear function subject to linear constraints, and this can be, actually can be shown to be equivalent to a linear assignment problem, which is something known in relations research, and it can be solved in polynomial time. Okay, so this is an example that shows you how we can, this application uses all the concepts I've introduced so far in this first lecture. We have seen Dempster's rule, the vacuous extension, and this very important idea that for very large problem, you may not need to compute the combined mass function. Okay, you may just need to multiply the contour functions, okay, to aggregate information. And okay, so these are some papers. And okay, so this is a chapter in a book that was published recently that gives maybe a more recent account of the Dempster-Shafer theory that in Shafer's book. Okay, so it's title was Beyond Probability and Representation of Uncertainty in AI Beyond Probability and Possibility. So we treat belief functions and imprecise probabilities in this chapter. This is the paper about the cautious rule. Okay, I didn't speak of the cautious rule today, but Frédéric will do it this afternoon. And this is a paper with that object association idea. If you want to know more about this, you will find all the details in this paper. Okay, so thank you for attention.